Hello everybody! In this clip we construct out of a given lattice fan in a covariant manner a toric variety. The idea behind this is to glue all the affine toric varieties which are given by the cones of this lattice fan. Let us look at a simple example, the projective line. Classically it can also be obtained via gluing two copies of the affine line C along the open subset C star. Then one has to be careful how to identify the points here. In order to get P1, the rule is that one identifies Z on the one side with 1 over Z on the other side. The toric gluing avoids this complicated identification process in a certain sense. Here is an idea. In this example, the right-hand side, C, let us regard it as C star plus the point 0. The left-hand side is C star plus the point infinity. Now one glues these two things along C star and no complicated identification anymore. What does this mean in terms of cones? C star is given by the 0 cone in Z, and this C star plus 0, so C is just the positive ray, and the other thing, quite intuitively, is the negative ray. The 0 cone is a face of both, and it is an intersection of these two rays. So if we fit them together, we end up with a fan, and this is the fan of the projective line P1. So in this sense here, the fan manages this in general complicated gluing procedure for us. The first step in the general gluing procedure is to understand the geometric meaning of the fact that one cone is a face of another one. So look at the lattice cone sigma in M, and let tau be a face of sigma. That means that tau is cut out by a linear form U from the dual cone, and we may take U to lie in the lattice. Now we need the toric variety associated with this cone tau. First step is we have to find the dual cone. This is the basic rule of dualizing an intersection. It is the sum of the duals. So we have sigma dual, and here we have the line through U, and also the sum gives our dual cone of tau. Similarly, for the cone monoid, dual cone of tau intersected M is sigma dual intersected M, and what is new are the integral multiples of U, in particular the negative multiples are new. They are not contained so far in sigma dual intersected M. What does this mean for the associated monoid algebras? The monoid algebra tau dual intersected M is the monoid algebra of sigma dual intersected M, and what is new are negative powers of chi u. So what we obtain here is the localization by chi u. Geometrically this means that x tau is a localization of x sigma by chi u. This procedure obtaining x tau as a localization x sigma is entirely toric. So summing up everything, we end up with a toric open inclusion of the toric variety x tau acting torus Tn x naught inside x sigma Tn x naught, and the first map is just inclusion, and the second one on the acting torus is the identity homomorphism. We are ready for the general gluing construction. Consider a lattice fan sigma in N. Then for any two cones, small sigma prime, we know that the intersection of the two of them is a phase of both. By what we have just seen, that means that the variety associated with the intersection is an open subset of both of x small sigma and of x small sigma prime. Now define x capital sigma to be the gluing of all these x sigma prime along the x associated with sigma intersected sigma prime. Then, by construction, the affine varieties x small sigma are all open subsets of our x capital sigma, and moreover the intersection of any two x sigma intersected with x sigma prime is the place where we glued these two together. That means x sigma intersected sigma prime. Let us study a bit the object we just constructed. It is a basic fact that any two cones, sigma and sigma prime, of our fan admit a separating linear form. That means a linear form U, which is non-negative on the one cone, non-positive on the other, and it cuts out from both their common intersection. Geometrically, this means that the intersection of these two affine varieties inside x capital sigma is the localization of x sigma by chi u, and as well the localization of x sigma prime by chi minus u. This minus is due to the fact that here we have non-positive values only along sigma prime. So, but this means that we obtain a surjective multiplication map. The functions on the intersection x sigma and x sigma prime, they can be all obtained as products from functions here and functions there. What is missing in these functions compared to Ox sigma are the negative powers of chi u, because it's a localization. But these negative powers of chi u, they stem from here. So this is a way to characterize a separateness of a variety. That means that our x capital sigma we constructed is indeed separated. What else can we say about our variety x associated with the fan sigma? First, in the gluing process, we had a look at localizations, and these have been toric localizations. That means that all these inclusion maps are toric morphisms. So the whole gluing process respects all the toric structure of the input data. And so we end up with a toric variety x sigma coming with a Tn action and a base point x naught. The next thing are maps. Given a map of lattice fans, sigma and sigma prime, then this means whenever we have a cone sigma in capital sigma and also sigma prime in capital sigma prime, such that f maps sigma into sigma prime, then this gives us a toric morphism of affine toric varieties. These toric morphisms between the affine pieces can be patched together and give a toric morphism from the toric variety associated with the fan sigma to that associated with the fan sigma prime. Everything we have done can be summarized in the following theorem. It says that we have essentially inverse covariant functors from the world of lattice fans to the world of toric varieties and back. From the lattice fan side, we just do the construction performed some minutes ago. And the way back, we have seen earlier, to a toric variety, we associate its fan of convergency cones living in the lattice of one parameter subgroups. And to a toric morphism phi tilde, we associate the push forward with respect to phi tilde of one parameter subgroups. The theorem we have just seen is the starting point of toric geometry. Toric geometry means to link concepts from the combinatorial world of lattice fans with concepts of the geometric world of toric varieties and also back. Let us, for the moment, look at a particular example to get an impression how this toric geometry works. Look at the following map of lattice fans. There is a fan sigma A, depending on a parameter in Z2, with 4 maximal cones, and these generators of the rays are 1, 0, 0, 1, minus 1, minus A, 0, minus 1. There's an obvious map onto the fan of the projective line, and we would like to understand what is this geometrically. The situation is covered by 2 parts. One is the right-hand side of that fan, and one the left-hand side. The right-hand side looks quite familiar. This is a product fan, and below we have the fan of the affine line, and above the fan of C times P1. So this just represents the projection from C times P1 to the first factor C. What about this left-hand side? It's not so clear a priori. However, if we multiply with this matrix, then we end up with something again familiar, again a product fan, and this is another way to represent the projection from C times P1 to C. The fact that this matrix, this integral matrix, has an integral inverse means that we have a toric isomorphism here between these 2 surfaces. So what we obtained at the end is a toric variety X sigma A, which maps onto P1 via a toric morphism. And this map is locally the projection of a P1 bundle. So we obtain in total a P1 bundle over P1, and the surface X sigma A is a well-known object. It is called the A's-Hirzebruch surface. See you in the next unit.